Mathematica. So now, I think other day, if you remember right, we have just seen up to this error function. Yeah, this is what the function which we have seen, and we have plotted this also, and we have plotted separately sin x by x. It's a sinc function that also we have shown. And when you do that integration, we can specifically mention the name of the method that you wanted to have, and working precision that is also possible. These things we have seen. So again, further we continue with this numerical integration. So the Mathematica cannot evaluate this definitely using integrate, but can numerical evaluate using the /n or n integrate. That's the. So if I enter this as it is, this is the equation which we wanted to integrate with the limit x varying from 1 to 10. So now it started. So you are getting back this expression. Okay, it's indicating that integral 0 1 to 10 sin square x tan x divided x into dx. Same thing, it is given it back without integrating. Okay, and this is available in the form of a numerical method. Okay, you can ask for /n, which gives the numerical value, or you can ask for n integrate. They are one and the same. Okay, this is when you have a problem with kind of functions that as it is doesn't integrate, the numerical things are possible. But please remember that numerical also there are limitations. Should not underflow and overflow should not happen with the limits. Okay, otherwise, Mathematica will give an error or it will indicate that it's underflow or a overflow. Okay, now the series you can expand using the Taylor series. Use series to compute a Taylor series expansion of the function. Say, for example, this is the function. You have x power 5 e power x square minus 1 about x is equal to half 2 up to x minus half whole cube. Apply n numerical value to see how output changes. Okay. So this here now series is this. This is the series we wanted to expand it. 1 divided by x power 5 exponential x square. See, exponential x square minus 1. This is the denominator. X. We are expanding about the point half up to 2 powers of 2, where you can see 3 is going to be the component of the error that is possible in this Taylor series expansion. Okay, now the equation 1, which is expanded now. We already found the answer, and we are applying numerical value of that, and this is what the value we have, and you can find out for a given x what is the value of this series. Okay, this is the approximate. So now suppose if you don't want to see this, you put normal. Maybe that will show you without the, so that error component has not been shown. This is the normal form. You see the difference between this and this? Maybe you can copy, edit, copy and paste over here, and remove this normal. See, this is what the result with this form will disappear if you ask to put it in a normal form. Okay, right. So, and we can have number of terms can be even more. For example, I can have it as something like 8 terms, and you will see the corresponding series. Then 9th term is this is the error component. Okay, so error will get reduced when you expand it. Okay, so we will analyze the error component afterwards. But please remember that when you go for higher terms, then the error component will go down. You can see all the terms that are available expanding around half. Okay, now we can also find out what is the equation with the numerical value. This is what they will give a next value and put it in normal. It's expanded up to x power 8. And you can give any function which can be expanded using Taylor series around a given point. You can expand it at any point you like. For example, I can expand around 0. Okay, this is what the expression, expand it around 0. This is what the result. And we have expanded previously for a half. I can expand it to 1. Okay, so this is also again options for you, and that can also be explored. Okay, so let me reduce this number of terms to the 2 itself so that it can be same as what has been given in the notebook for learning the Mathematica report. Okay. Okay, expand the function 2 divided by x plus 1 by 3 about infinity and 1 plus 1 divided by 1 minus x square about 0. Use both the notation series x of 0 power n. Eliminate the order symbol with the normal. That this order symbol can be eliminated with normal. So 2 equations are there, equation 1 and equation 2. And this, you can see this is blue, this is equation in a black color, which means the equation already been defined, but it doesn't matter. We are going to redefine with this equation 1 with the first equation what we have. This is the second equation. And we are making a list of left hand side equal to the right hand side. It means equation 1 is this, equation 2 is this. Even though previously it is defined something else, now it is reassigned with the equation 1 with this new value of this expression. A new function will be assigned to it. So equation 1 and equation 2 is what so that's what is given here. Now see this equation 1, okay, infinity about infinity. What is
Now the black color has been
black color has been disappeared, or both?
blue color.
Blue color disappears. Both has been redefined now. That the equation 1 is redefined because equation 1 already we are used here now. That's why it's appeared as a black here when even though it's entered. But when I enter it here, this equation 1 is replaced by this. That is what is given here. Okay, it's no longer a equation of this one. It's now the latest defined equation or expression. Okay, now we are going to expand it. One of them is about infinity, and other one, okay, about 0. And this is what the results that you have for this series. Eliminate the order of symbol with the normal. So just put solution 1. Probably you can see here. This is number 1, 2, in which add this normal, which eliminates this approximate value of this O x power 15 and O x power 6 that being taken out. Okay, this is what the normal expression. Okay, I think it's clear for you. And you can expand around any value of interest. See here we have expanded this expression about infinity. Then this has been done. Now, another interesting.
Sir, can you make it 150% so that it would be visible more?
Oh, sorry. The screen size. Yeah, is it clear now?
Sir.
Is it okay?
Yes, sir. Yes, sir.
It's 150 now. That's right. Okay. Fine. So let's go to the next one. Determine the following limit: x goes to infinity 1 minus 1 by x whole power. Do you know these limits? Are you familiar with this limit? Very interesting function.
If you can say a few words, that would be good for the student.
About this
Limit.
Yeah. So this limit is well, you have already familiar with the displacement when you differentiate. You're going to apply a limit, right? Do you remember that? What do you mean by differentiation of the function? Change x by a small amount del x plus del x. What happened to the y? Okay. What happened to y? Y becomes It's an effect of del x on the function. So correspondingly, y also get changes by the factor of del x. When you change the function, say for example, I have, well, I think I should show you the function which you already learned. 1 minute. That will be clearly explained to you what is the meaning of a differentiation, which we have done it already also. Session 8 itself we have before dynamics of object. Where is the sign function? Define somewhere here. I think I have taken it out.
Sir, that you have already taken. Then finally it is matching with the
That is what you are trying to do. Exactly, that's what the meaning of the limits. The limits del x go to, the limit del x go to 0. You will get a final result. Same logic that we are going to follow here. That is what the limit which you are going to do. Okay, so we are going on limit when x is increasing. 1 minus of 1 by x, the whole power x, this x is sitting in the exponent and also 1 minus of x. And this will be converging. And this is a fantastic number, you will get it. You notice this number? Okay, he has given in fact both of them. You can see this, change the sign here. Change the sign here. Okay. Now you see this is going to be an interesting number or interesting function which we are familiar. This is going to be a 1 by e. This one is 1 by e, which is e to the minus 1, and this is e with the plus sign. And in fact, another way to get this with the limits of e. See what's going to happen now. I'll take this one, put it over here, and x, we'll make 1 by x here. You see what is the difference which I'm going to do? Let's see what's happening. But the limit, instead of x going to infinity, I'll make it as 6 equal to 0. Here again, I'll make x, and this is going to be 1 by x. And see what is happening now, x equal to 0. You see? You see things? Amazing. That's the beauty of this, the limits. I just taken this as an exponent and shifted to this at this place. Same thing is done here also. I'm getting back the same thing. E power minus 1, e. Okay. You get the functional form. Okay. 1 minus 1 by x whole power x. Here 1 minus x whole power 1 by x, but the limit has been changed instead of infinity. If I put infinity, then you won't get the. Let's see what's happening. Escape INF. Okay. It's become completely different results. Okay. So therefore, limit should be correspondingly converted so that you get back this 1 by e. This e power minus, which is nothing but exponential. This is the, I wanted to evaluate this numerical number. This is going to be e. It is a number which never ends. You are all familiar already, like pi. This is the number. A rational number never ends. You can have any number of digits. That's the beauty here. 10,000 digits already you have. And as you did it for the pi, okay, you can do same thing here. Find out after the decimal how many ones, zeros are there, how many 1, how many 2, 3, 4, 5, 6, 7, 8, 9. How many are there? That can also be found. And you can list out these numbers and see what is the order in which you are getting it, how many number of digits that each one is contributing to this, this rational numbers that can also be analyzed. So this is a very important number, 2.71828. At least to this extent we should remember. Okay, so this is the beautiful number now. For the same number, we are able to get it in various forms with the proper limiting cases when you apply. Okay, and this can be can we expand this in the series expansion? This E can be expanded. Well, it's a number. Okay, can I do that? Is it possible to do this series expansion on this E? There it is. We have done something here, series expansion. Yeah. Here. Maybe have here also. So series expansion, let me take this one. So P there and put it over here for a E and see what is happening on the E. Double stroke P. Okay. We'll make it X. Starting from 0 to 14 now. I'm getting it. Okay. Now what I supposed to do to get this number? E should be, what I supposed to do afterwards? Substitute X equal to 1. Correct? 1 is not a valid number. Why? Why not? Okay, I think you have to expand it and then make a substitution. See what's happening. That substitute here X is equal to 1. 1 is not equal to 1 is not that. Then what will be thing that can be done? So there is 0, 1, which we know. And if I take e power 1, that's going to be the number. Ah, that's right. So, okay, this is what the problem now. Oh, wow. I'm not able to even delete this. Make it normal. Eliminating that, then this can be removed. I want to just check where is that. X equal to 1.0. It should take, what is great? Yeah, they're getting it 2.71828. Okay, is it right?
Okay,
So,
sir.
this
Sir,
is
what happened in the previous case, sir?
What happened to the
The
previous code? Yeah, that's right. So if I don't use that, okay, this component we do not know that error component we are not evaluated and substituted here.
sir, why that component came? Because here we x
No,
0,
no. Please note down. This is a fantastic number. It never ends. Okay, and
okay, sir.
you should have an approximate 15th term. What could be the error corresponding that? There is going to be an error in your limitation of your computation.
Okay.
That should be known. If you add that, then that will be automatically appearing. Right? So
Okay,
this
sir.
is missing. This is missing. Even if you write 4 terms, okay, you can see that this is 5th power of that. There is going up to 4th power you have taken. 5th power there is going to be a error contribution that should be evaluated, and it is possible for you to evaluate that also. It's not a big deal. How do you do that one? By the way, how to do that one? Any guess? Anybody can suggest for this? No? Just think and suggest. Is it possible for you to find out what could be the error between this 4 and 5? Series expansion up to 4. I wanted to find out what could be the error contribution when the series expansion stopped with 4 and stopped with 5. Any guess? No? It's too difficult?
No, sir.
So I'll make it normal. Right? Take this and out. Put it over here. Okay. Normal. Close down this together. And put a minus sign here and make a 5 here. That's all. This is expanded up to 5, this is up to 4. And this difference you are going to find out or the value of, put the curl bracket here and substitute for both of them. X is equal to 1. Let's see what's happening. X is equal to 1. Which you should always try to think and explore wherever possible like this. See the error. See the error? This is 5, this is 4, this is the error. If I go make it 15, then 14, will it go down or not? See? 10 power minus 13 error has come down enormously. Agree with me? I do not know whether you were able to follow what I'm trying to explain.
Sir, error means whatever is the remaining.
No. This series is never ends. No, you are limiting yourself by 14th x power 14, and the x power 15 will be there. If x power 15 is number of decimal accuracy is much higher than x power 14. For example, x power 14, x power 15 accuracy is differed by this factor. If I make it, for example, you can see the 2 or 3 and 2. Look at what is happening. Because these are series expansion of the terms, and the error is 0.16667. Huge error, no?
Sir, if you are going to higher,
Yes,
so
higher polynomials,
error
if you
is
take it, the
decreasing.
error will go down.
Oh, okay.
That's what it means. Very simple. That's what the error analysis which you try to do that. And by putting it, the number of terms here, you can clearly see how the error going to change. See, for example, I wanted to make it as n plus 1. And I make n. You see how ideas can be expanded. Now I am making it, this is n. Got it? And make a table in which we're going to see the n is the number of terms. Okay? This is the number of polynomial order which you are going to retain. Then each time you are substituting x equal to 1 for, let me take n starting from 2, go to, say, let me take 25. Can I do that? Not a difficult thing at all. Close this bracket and look at this. What's going to happen? So x power 25, when you come from 25 to 24, this is what your error component. So nicely you can see how when you take the number of orders, polynomial order higher and higher, error can be. See, 10 power minus 27. And if you go beyond this, for example, I can have a number up to 50, because it can evaluate even up to 50 and show the numbers. 57. Okay. Look at the number capability of this Mathematica. You can have, it finds, you can see the difference in here. So 2 orders in the 10 power minus 65, this is 10 power minus 67. You can go on like this. Okay. You can go on like this. 150, 158, 160. So which means we are able to find out accurately to the power 1 power minus 60 by taking 100 terms. And that error can be calculated. So therefore, when you use the series expansion, make sure how important is the number of terms that should be considered for your expression. Take care of that and take that many number of terms and then analyze it. Otherwise, there will be a lot of error, and the error will start accumulate when it is put in this iterative use. For iterative purpose, suppose this number is used, you have an error that will be very, very small, even when you do it iterative. But here, suppose if I start here somewhere here, if I put it the same expression in the iterative form, then error will get blown up when it is going for a 50th iteration and 100th iteration, then error will be much more than your actual value. That also will happen. Therefore, you should be careful about for a given function to what extent one should take the terms that should be decided, and accordingly you take the number of the terms and then analyze and use it. Otherwise, if that number goes into iteration, then you will have a problem. And then you start interpret your results, and with that number what you have, then you will be ending up with the wrong interpretations. Therefore, it is important to realize how many terms that I should consider for the computation purpose, depending on the problem. That's what the problem. Okay, that should be taken care of. So is it clear for all of you now? I hope.
Yes, sir.
Yes, sir.
See, now you see how simple is this thing. Nah? I am able to get it within no time what I am interested to look at it. And this function also I am able to get it. And you can plot these functions also with by incorporating the more number of terms, and then see how the plot is improving. It means your number is also getting approaches to the value of E, which is the number 2.7828281828, it's going on and reaches the accurate value. Okay, so this is the very, very comfortably that can be handled by using this Mathematica codes, which have been already developed. And you see how much we are, see, just series alone, we are not bothered. We want to do much more than that. We are able to do much more than that what we want to do. Okay, so that's how things have been. This is not something which should be available in the textbook. No, not necessary, because you have to think with the mathematical code which you have learned, which I have learned. I never seen this kind of analysis giving in the textbooks, which I have learned. I know how to do this. I'm just exploring it by putting an integer here in an iterative form. By taking the number of terms, I'm able to visually, I'm able to see the numbers directly, and which gives a clear-cut picture. Yes, when the number of terms goes up, the error goes down. Even up to 100, I'm able to see. Okay, even you can go to thousands. Doesn't matter for me. So it can work, it can handle. Okay, that's fine. Right. This is, so therefore, remember that this is a very important, very interesting function with its limits. And I have given alternate way also. Okay, changing the x equal to 0. So you know what I did now? When I was looking this one, no, I do not know even this result. It's result. This one. Okay. For a curiosity, I just felt, okay, let me change this, what will happen. And when I tried this, I ended up with number 1. Then I felt, okay, then the limit instead of infinite, I make it as 0. Then I find that this is, I'm able to get back this one by the e power minus 1 e. And then when I search the books, yes, this makes sense. This is possible to get it. That's how things will be learned. When you have something like this, no, you should not stop with this, because this mathematics gives an option for you to explore it, whatever the other possibilities, which one can explore it. That's how this understanding comes, and then we'll refer to, oh, this is possible for me to write like this also. The limits are applied like this, then I'm able to get the same number which is available as this 1 minus of 1 by x whole power x and 1 plus of 1. Again, this is also sign exploration. Also has been done. So for example, I want to explore what will happen to if I put a minus 1 here and a plus here. Okay, this is another way to look at things. What would happen? This, okay, just it is a complex form of it, lying between interval 0 to 1. So therefore, it's ruled out for me that this cannot give a number what is expected. And here this is E. And if I put this, these are the, but like this, one can explore them also. Okay, and it's really challenging to know about what is so great about this number. This number, something amazing, like pi, E and pi. And immediately I started thinking, E power, which is bigger, or pi power E. And why should we think about it like this? or something very strange, which one should feel it and then try to think what you just a curiosity to know about it. Okay, this is the result I have. I have to ask for the numerical value and find out what is happening. So something beauty, it seems to be they are coming closer to each other. Okay, these are all the curiosities that one should have. Okay, guys, what are the additional thing which you are having in your mind? Okay, you are thinking that I wanted to see visualize and or I wanted to see that, then that should be immediately explored. For example, 55 power 56. It's a number. I'm just asking you to 56 power 55. The question is, which is bigger? How do you do it? You have a Mathematica, you have learned already some of the Mathematica codes. Okay? Which is bigger? How do you use Mathematica to check these results? You have to think now. Apply your logical mind and see that how do I verify it? Which is bigger? Okay? You can think and then formulate the equations correspondingly, simplify and tell, yes, this is bigger and there is a reason for it that can also be understandable. Can you make out that? Is there any possibilities that this can be explored and then give the result? One is simplest way because Mathematica can handle a huge numbers, is it not? So therefore, for me, it doesn't matter. I'll find out what is 55 power 56. That number I can found. I have found the number already. Okay, it's not a small number. I'll go to the next one. 56 power 55. Then I'll find out what is this big number. Where is it? This is the number. Okay, so can you guess among these two which is bigger? Without even I find
First one, sir.
first one because number of digits are more. Is it not? You can see it stops here,
Yes,
and
yes.
if you look at it carefully, it seems to be some 2 digits or more. So now what I can do is I'll take the number here, 55 power 6 minus 6 power 55. Search for the negative, that difference between them. That this is the difference. Huge difference between these two numbers. Okay. But is there any other logical way to check to say that yes, they differ? Is there any methodologies available for you to suggest yes, I would like to cross check this other way? Because you cannot do it with the other computational methods to show these results. Is there any way to do it? Any suggestions? Think it over. There is always a way. You can always find out that. You can precisely and locate that method also. Then you can say, yes, that's also right. I don't have to find such a huge number and find the difference to check whether which is bigger. Okay, that's a way to do it. You can think about it. I'll suggest think it over and we'll try to work it out in the next class. I wanted to think over it. Then tell, is there any alternate methods? Which is directly by looking at the result. Yes, this is bigger. Okay, think it over. Right. So you get the point now, and you can really feel that it's really powerful tools now. Such a huge numbers. The difference has been found exactly here. This is the difference between these two numbers. You can select any number. I just given this randomly. You can select any number. 74 power 75, 75 power 74. You can select it also. It doesn't matter. Any number you can do. Then you can analyze them and you can arrive at a conclusion that this happens. This is the research. That's also possible for you to arrive at. Okay. Right. Fine. So this is connected to the series, and these are the Mathematica code that can be explored. And here you are going to think for a Mathematica code to do alternatively check which is bigger. That you have to think it over, mathematically formulate, then work it out with this Mathematica and tell this. So now we come to the range and tables. Okay. You can see this statement by range. You can do great things with this range. So you can see what is the range here. Half to 9 by 2 steps of quarter. Hello? Half to 9 by 2, which is 4.5, and go in terms of quarter. So half, 3 by 4, 1, then 5 by 4, goes on. Gives the numbers ranging from this to this in steps of 1 by 4. All that are available. Okay, so now table X. Okay, table X. See, range gives only one statement, which is tabulated here. I'm going to use a table X, X starting from half to 9 by 2, the end value, then increment of 1 by 4. They are one and the same. So I don't want to even do this one. When I want to have such series to be written, use the range. Okay, a range is available for me to use. Okay, and there are very many options available for the range that can also be explored. Okay, so this is how the range is available, and you can see the options that are available for the range. You can see 1, 2, 3, 4 options are there. And this is all listed out here, and how to explore it. Range 4, 1, 2, 3, 4. Range 14. I have 1, 2, 3. Okay. And this is with the decimal. 1.2 to 2.2 increment by 0.15 up to this 2.1 has been expanded. Similarly, x2, x plus 4. Okay. That also again. Range has been covered completely up to 4. So there is a scope for it. Incremented by steps of 2 minus steps of 5. See that 0, 10, n pi with the numerical values, and here is the range. Okay, from this to this plus 5. That's for the number. Okay, so 32, 33, and 225, 2 power 25, 2 power 25 plus 5. Okay. You follow what I'm saying? This number alone changes here. You can see incrementing by 1, 2, 3, 4. They differ by a factor of 5. 1, 2, 3, 4, 5, 6. Of course, 6 of them are there. 2, 3, 4, 5, 6, 7. That only number which is different. Because you are going incrementing, going this number plus 5. That has been shown here. All other numbers are identical. So whether it's a big number or a small number, that doesn't matter. It can be the range, and it starts from here and ends up to this plus 5. So you can see this 2 and add another 5, 27. That number has been found. Generalization has been given. Applications are given. Random sampling or suggestions are there. Properties and relations. Issues are there. There are some issues will come. We should be careful about that. Complete examples. Okay. So this is how range is being handled by Mathematica. Okay. And you have a table that is equivalent. But this is an improved version. The table is the older one. The range has been added the later versions. Okay. So now come to the list plot now. Use a table to generate the following set of data. I want to have a following set of data. And I and I plus VA are variable square of that. Where VA is random real number between 0 to 3. Okay. We need to have a random number real numbers. It should be only between 0 to 3. Then I is lying between 1 to 10. You don't want to have more than that. Then define the replacement rules that transform the data as follows. This is the rule. transform it. Replace this by this confirmation. And then use the list plot to display the transformed data. Okay, so let's see table I. You have a random reals which is lying between 0 to 3 and then square of it. So I varies from 1 to 10. That's what it says. I varies 1 to 10. These are the numbers that have been generated. Okay, so let's see. This is the numbers. You will not get the same number because every time we are calling a new random numbers. Okay, fine. Now, point SPT is now, this is replaced. You see, this VAR variable has been replaced by a same thing what has been given here. This is a rule replacement. Substitute here, and you would get the similar results here. But of course, the same results cannot be produced because random numbers are different every time. Therefore, then you are using a replacement rule as he is suggesting here. Okay, replace this, okay, by square root of 5. You can see this replacement again given by an underscore here, underscore here, underscore here, so that goes automatically into this place. Okay, this will all become automatically variables. Okay, into this, and the number will be evaluated. So replacement rule, the functional form can be done by using I underscore, which is equal to the square root of I, and then the second one is I plus and I underscore plus variable underscore whole square equal to log 10. I think he has asked for log 10. Yeah, log 10. Base 10. I plus variable square of. So if I put the variable random between this, you will get this number, set of numbers. Set of numbers. That you can plot it. That's what is asked to plot. Plot it. This is the number that is generated. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data from 1 to 10. That is what has been done. So now you can see the table list plot. Tables can be created, and also you can use the rules for varying it automatically with something else also. Then make a plot of that points, whatever they are getting. Either you can plot this also, and this also can be plotted. This is what the Mathematica code for a table and the list plot. The tables of planets. Here, the data for the planets. The mass, semi-major axis. Third one is period. Fourth one is eccentricity. It is given by the following 9 lists. The mass. Second one is the semi-major axis. This is in meters. And this is the period in units of years. For Earth, it will be 1 unit of 1 year. And the unit of year, this is 0.241 years. This is 0.615 years. This is 11.9 years. This is 1.88 years. This Saturn is 29.5 years. This is 84 years, and this is 165 years. This is 248 years. This is period, and this is the eccentricity. So they are small numbers that really matters. Okay, these are the data. What is that supposed to be done? Where the units are kilogram, semi-major axis. Okay, M, period Earth years. Okay, part A, display the data using the table form first. Display the data, okay, in the table form. So you have to enter all the data now. Okay, then define it for each planets equal. The list is containing this parameters. So you enter this list will be available for you in the form of a matrix with this quantities, mass, major axis, period, and eccentricity. And they have defined what is what. So list is this. What is this list? This is the planets. 1, 2, 3, 4, 5, 6, 7, 8, 9 planets listed. Now here table form list. This we have defined here. Each one has been already assigned. That we are making as a list, and that list is contains this equal values that are available. So let me show you this separately. What is this list now? In this in here. So V and I'll 63 already entered. We have take out this and look at this. It is available in the form of a list what has been defined there. Okay, is it clear? If I put a semicolon, I don't want to see the output. Fine. Now we can go to this list can be put it in a table form like this. I wanted to make a table form so that it is clear for each one of the planets. We have the corresponding parameters. Okay, what do you do? So table form, that list should be appearing. Table spacing will be 1, 1 between each one of them. Headings will give Mercury, same order. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Then the other parameters are mass in kilogram. Okay, semi-major is in meters. This is years per year, Earth years, and ECC at centimeters. Now we have this, and shift enter it. If I do that for this, I get this table. That is what he is asking to do. So you know how to create a table, set of data that are available for each one of the planets. That is what is going to happen. So then this one, table form, list has been taken here, spacing is here, table headings are there. Table headings are given for something like you have this column and this is the row, and it has been transferred to the form of a data table. It's available for you. Okay, and here you can see we are putting in a scientific form with the 3 digits. Okay, with an exponent. For example, all will have 3 digits. If this third digit is not available, that will not be shown. Okay, that has not been shown. Okay, suppose if we add same thing with the 4 digits. Okay, that's also been here. Okay, so this is what the solution have. So here is enough to have 3 digits and give the data. This option again. Okay, scientific form of this. This is hash for all the set of data. Apply the scientific form and hash. This and symbol takes care of that. For every one of them, that is applied. For every one of the list, Mercury, Venus, Earth, and etc. Okay. So here is the table. Generate a list of integers, square of the integers, and cube of integers. Display the result using a table form. Generate a list of values for log x, natural log, log 10, x. This is log base 10, and log base anything. This is 11. Display the numerical results for different values of it using a table form. Look at the solution here. Option table forms. These are the options which we are making it now. You see, hash, square of the hash, cube of the hash. And what does it say? You have integers. So range will tell you, okay, we are going up to 1 to 10. Okay. So which means on this list, okay, at this Mathematica code, repeat it for the range what has been expanded. So this automatically takes the numbers, the square of the numbers, cube of the numbers. It is very, very compact form to write it. Okay, over. Then put it in a table form of this hash will be there. table alignment which is centered, table spacing is given, headings. See, this vertical thing is not there, only the horizontal thing, table. That's table heading, this is empty, and integers, squares, and cubes are here. This is being centered. That's what's centered. So you can see that it's possible for us to get these things in a compact form. Table form is the option. All that we need that has been given. These are the table form options. Okay. So numbers and squares and cube has been listed up to range. Now this range can corresponding range, if you make it as 20 also doesn't matter, it will give automatically. Okay. It goes automatically without having any difficulty. The square and cube. So this is what the thing that happens. Now the whole thing can be, I wanted to have a the other side of it, I want to have integers, squares, and cubes. And here I wanted to see all the numbers on the integer first, square of the second, and third one is going to be the column in these rows. What do? You transpose this. See, transpose. Okay, put the same thing. You know, you can see integers, squares, and cubes are available. Integers are here, squares, and cubes. But this is fine. So you can make it, but also up to 20, that can be seen here. You will be getting it now. Okay. So it's very easy to handle the tables also. Whatever the way you like, you can do it like this also, and then you can do this also. So column wise, this is the row wise. The tables which you write it here now. This is integers, square, and cubes, which have been. This is an additional statement that has been added here and closed it. Table form, and the transpose is done here itself for this 20. Okay, this is what the thing which is converting in the table form after generating it. So if I take this and look at it, what do I have is only, let's see what's happening now. This alone is this. Okay, and the double slash table form is the other part of it. It is applied here by using this. This is again for all the number that you have, apply the hash and then follow this instruction. Create this. Done. Similarly here, for a log, natural base is base E, that's hash. Other one is base 10, and other one is base 11. Then and at. This is the at is not the list here. Not instead of range, I have three quantities in the list. That one by one it is be applied. First one is natural, log G, then 10, then 11. You can see that has been applied here, and you will have to get it. Of course, we are given in the transpose form. So that's why 1, 2, 3 is here. Then you have a log x 10 and log base 11. Numbers are available. If you want to have a numerical value, put this. So that is easy to do it. Take it and pt numerical. Yes, done. And one more possibility I wanted to see. You can see the numbers here, number of decimals. Is there anything can be done here? I want to check whether this will work here or not. I think it should work. No, not working in this place. Not added. Spelling mistake. Added form. It works. You see the difference between the previous one to this? It's important. That this is also another important statement that one should learn when you are doing the tables. Edit. So P, look at this. Previous one. Without this added form. Okay, I'm giving a product form 3, 3, which means 3 for the integers if we have plus 3 decimals. Okay, with that accuracy that can be given here. For example, 0.289, this 0, 1, 1. So therefore, all the 3 digits will be given. Fourth digit is not greater than 5. Is there anything which is greater than 5, fourth digits? No. Here is the fourth digit is greater than 5. Therefore, you see that 0.699 you will see. It's approximated that also. And here, no. Fourth digit, this is the fourth digit is greater than that. 1.098 instead of 98 into 99. 1 point. Very good. 1 point. Oh, okay. This is again taken another. So you can see fourth one is 1.38. It becomes 900. 90. Okay. And here again 1.100. So when you ask to do standard form, it takes all the digits into consideration. Convert to them is nearest possible numbers in corresponding digits. Suppose if I add 4 here, then that will also get modified. Okay. So it is enough to have 3 digits if you are starting with that. And number of digits need not be 3, but maybe 2 itself is enough. Okay. This is what the padded form of a table or a numbers. Any numbers that are available here, you can convert them into this table in this form and then make it that this kind of number of decimals which you are interested that can be fixed and then approximated also, and that will be tabulated in this form. That's the padded form, which is also additional Mathematica code that is available for the table purpose and also for number approximation. This is additional area. Points prints all numbers in expression padded to leave room for the total of n digits. Okay. Print the approximate real numbers having f digits to the right of the decimal points. Okay. Print approximate real numbers having exactly f digits to the right of the decimal point. So this is also required for us. And we get it. Now, you want to have any clarification with these things, whatever which you have learned as a Mathematica course? Okay. Any clarification? Can proceed to the
No,
next.
sir.
Right, very good. I'll go to the next part of it. Interesting next is products and tables. See this expression, fancy expression which we have. You have a product plus sum over. There are integers here. M is 1 to n, and for every value of n, there is going to be a summation n equal to 0 to p. That is what your definition of this function. So this should be defined in Mathematica. And take the value n is p equal to 1, 2, 3, 4, 5. Now we look at this. When p equal to 1, what happens to this? Correspondingly, you can see, let me take 5, g is 5. Okay. Now n takes a value starting from 0, 1, 2. At that time, correspondingly, n should be taken into consideration here, and that should also be take a product here to find the sum of this. So I think that's once p is given, n is known. For every one of the n, this summation will also be performed. Okay, and m is also sitting here along with that. Then this will be summed over with this. That is what being defined here in the form of f of p underscore minus x, because x is a variable here that can be used for plotting. Okay, so n equal to 0 up to summation to p. These are all available, as I said earlier. Palettes, you go to palettes, assistants, they are all available. The summation symbol over everything that will be. You see that somewhere? It's here. It's here. Product is here. So these are all available. click it and then put it over here. Okay. Now, take a finite value of P1 to 5. See, simplify table. Since we are using a table because P should be variable from 1 to 5. P is 1 to 5. We have taken that. Then with that, the first one is minus 11 by 2. Minus 169 by 16. 419 by 32. 14,000 dot 1024 and then 7 max 13. 411 divided by 51,200. This is what the number that you will be getting. The rest form. Okay. It's a really complicated expression, but that can be defined appropriately with the Mathematica codes which are available here and then put it over here. Define them properly. Take it over here for various values of P and then find out this number. Okay. Now, we're going to evaluate this. For P equal to 1 to 5, X varying from minus 3 to plus 3. See, whatever which you have here, for a given X it has been done. Understand? They have taken the X equal to 3. And for every one of them, value of P, this has been evaluated. Now, for any value of X starting from minus 3 to plus 3, if you make a plot, these are the plots that you will be getting it for the f of P comma X or P1 comma 5. So, you can see this is being evaluated here in the table form. What does it mean? Okay. What does it mean? I have 1, 2, 3, 4, 5 functions that are tabled here. This is for the table. I want to show the table here. Okay. This is the table. So, which we have not entered here, therefore, it should be executed here. Evaluate for a particular value of X. For any X, this is the expressions that you have. Okay. For any value, this is the expressions that you have. This expression, we can evaluate it for a plotting from minus 3 to plus 3. When you do that, this is what you'll get. These are the plot legends. This is the expression that is being used here for varying the X value that's being plotted. Okay. So this L0s are here already available as Bessel. There are some Bessel functions that are there in this. That is being evaluated. So which uses the special functions here. This is special functions, Bessel I, that complex form of the special that is being used here, and that is being evaluated, and you can see all the curves. And corresponding colors can be used here. See this one, this one. This corresponds to this. The plot legends takes care of that. Third and fourth and fifth, like that can be shown. Okay, so very complicated expressions which contain the special functions also that are all evaluated. So why do you evaluate? Because this is using a Bessel function, therefore you have to add, evaluate them for every one of the value of X. Then make a plot. That's the reason we put an evaluate. Okay, is it clear? I hope this is clear, and you don't have to really worry about the complexity of your expressions. Only thing, define them properly. Then you can make a plot. Next part is one small problem which is connected to the economics, which everybody is interested to know about this in terms of calculation of interests. Okay. So whenever you take an interest from a bank, they used to calculate that first by using some simple formulas. And here is the simple formula that is being used here, that is being explored. Then we have listed out the table form for the different interest. Now let's do this problem. If P dollars is invested in a bank account paying a rate of R compounded n times a year. This is compounded n times here, which means it can be 3 times or 5 times or 10 times or 100 times or every milliseconds or a microseconds. Micro, milli, nanoseconds, all seconds can be taken. So it is compounded n times a year. The amount of money after t years is t into 1 plus r by n whole power n into t dollars. Hold on. This must be an expression that you must be familiar when the high school's calculation of interest. The interest is compounded continuously. The amount after t years is t into e power rt. Look at this. This is the principal amount. This is the exponent e. W is to e power r into t. R is the rate of interest and t is the time. If $1,000 invested in an account paying 6% annually, okay, is invested in an account paying 6% annually, make a table showing how much money is in the account at the end of each year. For 10 years, if interest is compounded quarterly, monthly, daily, and continuously. Right? So what is it we are going to find? Now we are going to find out that for 10 years, we are going to deposit money of $1,000 in the bank, and then we are going to get the interest. This interest can be compounded, which means get the interest, add to the principal. Get the interest, add to the principal. That has been done by quarterly, which means every 3 months in a year. 4 times it's been done. Monthly, every month. Whatever interest that you have, you add it. That becomes principal. Daily, make daily. Okay, every day interest, whatever you have paid, you add it, and then add along the principal amount. Then second day becomes the first day with first day interest, then become a principal amount. And make it continuously. Continuous means how small is the period. Okay, that's option. You can do it the way you like it. Finally, find out what is going to happen. That is what this problem, and it has been done with a simple program. Here you can see this is the principal amount, and this is the interest 6%. It's going to be 0.06. This is R. Okay, quarterly means this should be done. There's an N here, there's an N here. Agree? Able to see here that expression what we have here? T into 1 plus R by N power NT. R by N quarterly. Okay, power NT means that N is number of times compounded. That is quarterly means 4 times. So this is what your quarterly money that you would get it. And you can see there is a padded form with the number has been taken. A is this quarterly. B is every month. Right? Is that clear?
Yes, sir.
Next is every day. 365. That is C. A has found, B has been found, C has been found, which are, this is quarterly, this is every month, and this will be every day. If it is continuous, every second, every microsecond, nanosecond, picosecond, femtosecond, you make it interest calculated. And that leads a formula P into exponential R into T. Okay, that's the number which we have. Okay, now you can now put it in a table form of this ABCD for the 10 years, 1 to 10 years. Okay, is it all right now? This is the padded form formula for this. So T also has been written in a padded form. TT is this one. Now, what is this? FAST. Fast. Table form is given fast. Okay. These are all written in a one single cell. See here. The whole thing has been put in a single cell. Therefore, you see there's going to be a semicolon here, semicolon here, semicolon, 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 semicolon. At the end, there's no semicolon, semicolon, the table will not be appearing. So, is there any confusion here? Everything is clear up to this. Okay. Then the fast is the table form. There you can writing. This table spacing is given. Table headings are. We are not putting anything on this y-axis, and we are writing on the top. Year, quarterly, monthly, daily, and continuously. That's what it is. So we'll try to see that what is going to happen now. It's been done, and this is the table. And you look at the numbers, and you can really see whether which is interesting to you. So, what do you prefer? So, which is highest now? For a 10 years period, the highest is?
For continuous.
Continuous. See, daily to continuous, you see the difference. About point, in fact, about 9 cents only is different. Okay, so you can see that this is how this. If I have a first year end, this 1,000 rupees becomes $1,000 become 1,061 if it is continuous. This of course differed with a very small amount, and here it's almost same. And this is quarterly. And quarterly and this also differ by very small amount. Go to the next one, second year, third year, fourth year, fifth year, like that. If you see, there's going to be a little bit difference. At the end, you find that continuously it has been taken means we have an advantage. If it is quarterly means there's not much difference, but there is a difference of about $6 or so. But ultimately, this is what the possibility, continuous interest if you take P into exponential RT. And do you find something interesting here? What we found the limits? The limit what is series expansion or limits now? We have seen similar kind of expression. Some number is there and similar thing is here. And you can say that leads to an exponential R into T. That number you have the highest possible interest that can be earned for any money that you are going to invest is limited by this exponential R into T. This is making a the so-called interest calculation continuously. Okay, and continuously means you will end up with this formula e power R into T. E into a power R into T. Okay, this is the natural growth. Doesn't mean that you will add every second of it or millisecond and it will become a huge money. No, it's not possible. It's happening only with the limit of e power R T, exponential R into T. Which means this is getting limited, and at the end you will get a number exponential times R into T. That is R sits here. T. The limit T goes to infinity. Okay. Or this number what you are going to add here, if it goes to infinity, you will get this number. Maybe you can try and check whether it's going to have meaningful results or not. You compare this, the series which we have here. The limit goes to infinity. Yes, control it here. So it's sort of, I'll make this as a infinite x, and this is n x. Can I do that? And then the limit limit okay. Try to take exact enough. Okay, both. Yeah, that's right. Is it the interest, no? That's right. E power, check. Rate of interest and time. And this is the principal amount. Fantastic. You are able to see that exponential. So natural growth is limited by exponential. Super. You're able to feel now? R already we have defined it. That's why it has taken 0.06. Is it okay? Is it clear for you? Let's clear it now. Clear the R now. Enter. Then if I do that, I get e power RT. That's the beauty of this function. Here it is supposed to be plus sign to get that. Okay. Already we have seen. A plus means you get an E. E power RT, I'm getting it. So how? That's what this. So now exponential goes and sits here in the limiting in your interest calculation, you end up with this. Okay. This is beautiful. You see how mathematics goes and sits in your computations. Okay. Really beautiful thing. Because I'm able to feel by looking at this expression, and x goes in the limit of infinity. Okay. Take some x. X can be anything. Okay. Then that's the time with that is going to be exponential r into t. That's what the limiting number that can. Okay. It's another interesting problem which can be understandable. And whenever you go to the bank, you apply this formula, check with the bank fellows whether they're doing a calculation properly or not. Are they doing quarterly or half yearly? Some banks they do 4 months once or 3 months once. Some of them will do it for half a month. And you can see there's a difference in numbers. Really matters for you. Okay, go to the next Hilbert matrix. I do not know whether you are familiar with this Hilbert space. And there is a matrix which has been found by Hilbert. That matrix is Hilbert matrix of order 5 that can be generated here. This equal to 1 by I plus j minus 1. Now the array that you are going to get it now, I vary from 1 to 5 and j is also varying 1 to 5. Which means 1 by 2, 1 by 3, 1 by 4, 1 by 5. Same thing happens on the row and the column. Then you can see the next one. Half, that's being repeated here up to 1, 6, 1, 7, 1, 8, and 1, 9. That is what this Hilbert matrix, which can be generated by using an array here, array statements plus defining this variable in this array. Okay, and you can change the ij initial values or this initial parameter minus one, any numbers depending on that, the matrix will get modified. Another interesting problem, suicide problem. It's really a very interesting problem, and you see how mathematical code can be developed for doing this, and then finally convert in a one-line problem and the result. Okay, look at this. Flavius Joseph was a Jewish historian in the 1st century. He writes about a group of 10 Jews in a cave who, rather than surrender to the Romans, choose to commit suicide one by one. You don't want to surrender them all the 10, but they can commit suicide one by one. They formed a circle and every another one was killed. And who is the lone survivor? Okay. This problem is clear to you? Flavius Joseph was a Jewish historian in the first century. He writes about a group of 10 Jews in a cave who, rather than surrender to the Romans, choose to commit suicide one by one. They formed a circle and every other one was killed. Okay, who is the lone survivor? So I think this problem should be understandable here. Then try to see, which means you should form as like a circle, start from somewhere, and then you see that every other one is killed, and there will be one fellow is finally surviving. Who is that survivor? That should be found. And of course, what is the starting point? That really matters. Of course, you have to start in an order. 1, 2, 3, 4, 5, 10 range. There are 10 people. This is for the hello. Previous so that will be a different list of places here. Range 10. There are 10 people now. The first person to go is 2. Every other person was killed. So now, let's see, this fellow will be going out. We eliminate him by rotating the list one position to the left and dropping his number from the list. I mean that fellow will be out. He's no more. He's been killed. Start with. Every other person should be killed. Okay, how do we do that? Rotate to the left. Rotate left, which means this list should be rotated. Previous is the list which we created. That should be rotated. Rotate what? Left, which means after rotating to the left, the number 1 fellow will come to after 10. So this has been, one fellow has been moved here. Then rest means the first one that will be dropped, will disappear. So rest will take care of that. So rotate left. See. What is this going to happen now? Range. And rotate. We have done the rotation now. Rotate left. It's been rotated. Below, and the first has moved to the last one now. So starting with 2. Rest means that first the list will be dropped. So that is dropped. You left with only 9 now. Okay? Is that right?
Yes.
Yeah, fine. Now repeat. Okay, so what do you do? Rest, rotate, previous, which is being redefined with this now, with the 9 people. Put it here. Repeat again. You can see. Rotate left. He is here, and that fellow, other fellow has been dropped. Okay. So
4 drop.
4 is dropped. Repeat it for the next. Next. At the end, you find the fellow who's left is the survivor is the list 5. This fellow is survivor. That's what's happening. You put them in this order, 1 to 10. That's survivor. So this is what you can see every time this is redefined, that has been taken and that has been operated again. You don't want to do this again, no, repeat. And there seems to be something which goes in an iterative manner. Why not we look into this problem, putting in an iterative form? Well, you are going to learn a new command now, nest list. Okay, rest is known to you so far. Rotate left also known, but nest list means on this list what you have the next that operate. Again, this on the same list you can operate, which means this list has become this list, operate on the next, like that. If you go at the end, you find this number 5 is left out. That's what is the result that you have here. One line, what has been written in a 10 different lines. See, rotate, hash, and range 10. Okay, range 10, and then next list. Okay, and this number 9, what does it mean? That you have to look into that. It's not something very difficult to locate, and you will see. Then column, hash, center, and column form you are writing it. You can see this is the column you are writing it. Okay, So now you can see the next list operating on this. Probably this should be done 9 times. That's what it means. Next list should be done 9 times. The 10th time automatically end up with this number. Okay, probably if I change, I will come from here. Start from here now. Range the first yes here. Rotate. Then sorry. This should be done again, second time, third time, 4, 5, 6, 7, 8, 9, 10th time. This fellow is lucky too. He has been survivor. He has been the survivor. Okay, now this can be done. Yes, I want to know what this 9 means. Okay, that 9 can be checked. Now I have to just complete this first, then copy and paste, and then give some other number, and I can confirm it. That is meant for certain purpose that can be identified. Get it? Okay. Put it over here and change the number as something like 6 or 7 or so. Iteration done up to 6. That's what it means. So 9 times should be iterated. If I do 9 times, the 10th color will be printed as a survivor. That's the purpose of 9. Next list is done 9 times on the range of 10 people and repeated this, and finally you have this number what you have. This can also be put in the form of a loop with a while statement and asked to write the same values can be written, okay, at the each time iteration, and finally who is left out is the survivor that we will be getting it. That's what the result that we have. Okay, this is what the result. And you see the number of Mathematica code that should be written has been come down to a one single line here. If you wanted to put in a loop form also can be seen here, but when you write it in a loop form, at the end what you have, that is something you are seeing it. But here able to see the intermediate steps, what is the process that's going on, that we are able to see. Okay, fine. I hope this is also clear to you that this helps you to improve your code writing skill, code writing skill. If you are understanding this, then I wanted to put it in a iterative form, either this or in this form. So there are very many ways that can also be written. Okay, so 4 o'clock, if you wanted to have some more, to only one I will show. This is quite interesting to see the animations. Okay, this is the pulse now on both sides, and when you can see this pulse is defined as fx t x underscore t minus sine of 3 into x plus 10 minus t exponential minus x plus 10 minus t whole square. This argument what you have, I have it here. Exponential square. So that I'll see the pulse. Here again, same thing, but the difference between this and this, you're able to make out the difference between this and this. This fellow is positive sign here. This is the minus sign. Okay. So which means the pulse on this left side and right side being obtained by changing the sign with respect to this position x plus 10 and x minus 10. X plus 10 means here, x minus 10, you are at the back side, the left side. Okay, fine. And this is which creates a pulse structure. This is the pulse structure with the sum sign form. Okay, now I will define this, enter it, and make a plot varying this at the time t equal to 0, there is a pulse. This is the pulse which you are getting. X varying from minus 15 to plus 15. So it is minus 15 to plus 15. Not range. This is 1. Y alone is range. And style is given. And axis filling. This is something new now we are going to learn. Axis being filled. Okay. With respect to this axis, whatever the curve which you have, that will be get filled. That is what the filling axis. filling style has been also given, up and down. Okay, there are two above that and below that. So you can see one of them is like a green, other one is a blue. And the plot style is red thick. So red thick thing that you have is connected to this. This is what the pulse is. Okay, if they start move, they meet each other, what is going to happen? With respect to the time variation, you can look at the what is going to happen. Do you have any idea? What will happen when they cross each other? What would you expect? Suppose they are meeting each other, crossing and then passing through. What would happen? That's what the animations going to show. It's a function of time. They're going to move each other together towards each other, 0 to 15 seconds. Okay, and this is instead of 0 to show, this is initial positions. Fine. Okay, and so the initial position is this, and vary it now. Super. We can see how things are going to change now. Okay. What is happening?
Constructive interference. Huh?
See, there's an interference, and the phase change also you can see. See, this is down now, that smaller one. It will be up when it is going back. You can see.
Yeah,
Down. See, phase change.
yeah.
Can you see?
Interesting.
Yes, all the changes. This is beautifully it's coming out when you try to look at this with the time animation. All very difficult to feel. Visually, you can realize it. Yes, phase change definitely occurs, and that can be seen. And also, when you interfere, the amplitude goes up. Is it not? See, the amplitude is rising. When smaller one meets, there's an amplitude rise, and even the bigger one meets also goes up. So all this consistently happens. And we can add them and see that these equations can be added. That's what the result that's going to happen during the interference. Okay. They're meeting each other and they are interfering. That can be seen. You can slow down it and look at it. Okay, we'll stop here. There are other interesting things like the algebras connected to Mathematica course that we will learn next class. So, any questions, any clarifications required? So, maybe I may require one class to explain everything about what are the options or possibilities that are available only on the main plate. Because
Yes,
that's a really powerful statement available in Mathematica for physics people particularly. There are of course other branches also. So I'm going to take one class fully with the main plate alone. All possible things we'll try to explore them. Then whenever there is a requirement to use them, you can use it. So probably next class some of them, I'll complete this algebraic part plus the main plate. With that we shift to slowly to the computational aspects. Because already we have completed 8 lessons over now. Another
Yes,
12 lessons we have. So we will start one by one numerical techniques. There also we try to learn some of the Mathematica course. Okay. Right. So I hope any questions?